Welcome to Unit 3, Lesson 8, Heating and Cooling Systems. By the end of this lesson, you should be able to demonstrate an understanding of heating and cooling systems by geothermal energy. You'll know you've been successful when you've been able to describe in detail the model's heating and cooling system by geothermal energy, and apply the concept to solve problems related to your daily life and to make connections within and between various contexts. So, conventional heating systems use oil or natural gas as fuels, whereas air conditioners typically use electricity. For convenience, electric heaters may also be used for heating homes. Every heating system must have all of these major components. They must have a source of thermal energy, a means of transferring the energy from one place to another, and a device that controls the production and distribution of energy. Conventional heating systems use either electricity or fossil fuels as a source of thermal energy, i.e., electrical heating systems generate thermal energy, which is transferred throughout a building by means of convection, while fossil fuel systems generate thermal energy by means of the burning of fossil fuels, such as oil or natural gas. Conventional heating systems use oil or natural gas as fuels. So some heating systems use the thermal energy to heat air, while others use the thermal energy to heat water. In a forced air heating system, a furnace is used to warm air to heat a building, which we can see in this image here. So warm air from the furnace is supplied to each room through a network of ducts. A separate set of ducts return cooler air to the furnace and bring in fresh air from outside to the furnace for heating. There's also an exhaust system to release gases such as carbon dioxide and carbon monoxide, so they don't come into your home. While there are heating systems that use the thermal energy derived from a source specific to the system to heat air, others instead use thermal energy to heat water. A forced air system uses a furnace to warm air to heat a building, whereas the warm air travels through ducts in order to reach vents that are positioned in the ceiling or floors of the building. The thermal energy also travels by convection. In this system, warm air that enters a room causes the cold air to be pushed through a certain set of ducts called the cold air return. This intriguing process allows for fresh air to be brought into the system while providing the furnace with more air to heat, all at the same time. While a forced air heating system uses a furnace as a source of its thermal energy that circulates throughout the system's network, a hot water heating system uses a boiler to heat water. This alternatively heats the building as a double purpose. The water is heated by the boiler as it uses electricity or burns fossil fuels to create a means to providing the system with hot water. This heated water is then pumped through the system's pipes, eventually reaching radiators located in the various rooms of the building. Conventional cooling system. The physics of conventional air conditioners, refrigerators, and freezers is very similar to that of conventional heating systems. These appliances use the evaporation of a liquid to absorb thermal energy from the air. A compressor firstly puts a special type of gas, called a refrigerant, under pressure. Whenever a gas is compressed, its temperature increases. The warm refrigerant goes through a coil of tubes where it starts to release some of its thermal energy. As the refrigerant cools, it changes into a liquid. The liquid refrigerant then passes through an expansion valve, moving from a high-pressure area to a low-pressure area. At this point, the liquid refrigerant absorbs thermal energy from the surrounding air and evaporates back into a gas. The surrounding air cools down as a result. Since the compressor of an air conditioner can get very warm, air conditioning units are installed outside the building, where the thermal energy can be released into the external environment. The only difference in the case of a refrigerator or freezer, although the same type of compressor and coil system is used, is that the cooled air is produced in the refrigerator or freezer and the warm air is released into the external environment. So the compressor in a refrigerator puts the refrigerant under pressure to change it into a liquid. When the refrigerant moves through the expansion valve, the pressure decreases and the liquid evaporates as it passes through the evaporator, removing thermal energy from the air. Both heating and cooling systems contain a thermostat to sense the temperature of the environment and turn the furnace or air conditioner on or off accordingly. Conventional thermostats contain a coiled bimetallic strip and a mercury switch. A bimetallic strip consists of two types of metal bonded together back to back. Due to the different types of metals, the two sides of the strip expand and contract at different rates when heated or cooled. Expansion and contraction make the coil tighten and loosen as the temperature of the house fluctuates. On top of the biometric strip is the mercury switch. Mercury is a liquid metal that flows like water and also conducts electricity. When the bimetallic strip coil changes shape again, the mercury switch tilts and the mercury moves inside. When the temperature in the building is above or below the temperature that an operator has set on the thermostat, the switch tilts in one direction and causes the mercury to touch two bare wires. This creates a closed circuit and turns the furnace or air conditioner on. As the environment warms up or cools down, the biometallic coil changes shape again. This causes the switch to tilt in the opposite direction, moving the mercury away from the circuit wires. This opens the circuit and turns the furnace or air conditioner off. So this is an example of a conventional thermostat. A biometallic strip is curled into a coil so that it winds or unwinds as the temperature changes, resulting in the tilting of the mercury switch on the top. Many of our thermostats now are electronic, and so they are measuring the air with electronics as opposed to this kind of coil strip. So an environmentally friendly alternative is geothermal systems. So the most popular methods of heating involve the burning of fossil fuels. This burning results in the release of greenhouse gases such as carbon dioxide into the atmosphere, contributing to global warming. The refrigerants used in cooling systems are also greenhouse gases and contribute to global warming when they leak into the environment. Some refrigerants also damage the ozone layer, a layer of ozone gas in the upper atmosphere that helps reduce the amount of ultraviolet radiation from the sun that reaches the Earth's surface. Damage to the ozone layer contributes to increases in skin cancer caused by excess ultraviolet radiation. To reduce production of greenhouse gases and protect the ozone layer, alternate forms of heating and cooling are being developed. One such example is a geothermal system, and it's just another way for heating and cooling buildings. One of the newest heating and cooling technologies makes use of the thermal energy contained within the Earth's crust. Geothermal systems use heat pumps to transfer the Earth's natural thermal energy for heating and cooling. Temperatures at a depth of 3 meters below the ground remain fairly steady throughout the year. Depending on the latitude, the actual ground temperature can vary. In Ottawa, the temperature remains about 9 degrees Celsius, which might seem cold, but can still be used to heat a building in the winter. During the winter, the temperature below the ground is higher than the temperature above the ground. In a geothermal system, a liquid antifreeze water mixture is pumped through a network of plastic pipe that is placed a few meters underground. As the antifreeze water mixture is pumped through the pipes, the thermal energy from the ground is transferred to the walls of the pipe by conduction and then transferred from the pipe to the liquid by convection. The liquid is then pumped into a heat pump located inside the building, which then transfers the thermal energy from the liquid to the air inside the building. Inside the heat pump, a liquid refrigerant is pumped through a series of coils. Thermal energy is transferred from the antifreeze water mixture to the refrigerant, changing the refrigerant into a gas. The gas moves through another set of coils where the pressure is increased. As the pressure of the gas increases, the temperature also increases. Air blows over the coils containing the hot refrigerant gas, and the hot air is distributed through ducts to warm the building. During the summer, the heat pump process is reversed. Hot air from the house is pumped over the refrigerant, causing it to warm up. The refrigerant then transfers its thermal energy to the antifreeze water mixture so that the water mixture warms up. Since it is cooler underground than above ground during the summer, the thermal energy is transferred from the antifreeze water mixture to the ground by conduction. So here is an example. On the left, a geothermal system. Thermal energy from below the ground is transferred to the heating system inside the building during the winter, which heats the building. During the summer, thermal energy is transferred in reverse. So the hot liquid is transferred from the building to the ground, which is then cooled by the ground and pumped back into the building, which is cooling the system. So we have a few definitions. Electrical heating system is a system that uses electricity to produce thermal energy for heating. A forced air heating system is a system that moves hot air to heat a building. Hot water heating system is a system that uses hot water to heat a building. And a geothermal system is a system that transfers thermal energy from under the Earth's surface into a building to heat it, and transfers the thermal energy from the building into the ground to cool the building. All heating systems have a source of thermal energy, a means of transferring the energy, and a thermostat to control the production and distribution of energy. Conventional heating systems use either electricity or fossil fuels as a source of thermal energy, and conventional cooling systems use the evaporation of pressurized refrigerants to absorb the thermal energy from the air, resulting in a cool air that can be blown throughout a duct system. A typical thermostat uses a bimetallic strip and a mercury switch to turn a heating or cooling system on or off as temperature changes. Conventional heating and cooling systems produce greenhouse gases such as carbon dioxide, so they are not considered environmentally friendly. Geothermal systems use the Earth's natural thermal energy for heating and cooling purposes. In the winter, thermal energy is transferred from below Earth's surface into a building to heat it. In the summer, thermal energy is transferred from a building into the Earth's surface to cool it. We've reached the end of this lesson, so please be sure to complete the quiz below the lesson. And if you have any questions, please do not hesitate to reach out to your teacher.